Okay, here we start working on some examples. In this particular case, we are being asked to calculate the speed of an electron that is accelerated from rest to a potential difference of 115 volts. They didn't explain what the potential difference is, but remember from what we have learned, for a negative charge, whenever Q is negative, it's going to accelerate when it moves from a low electrical potential to a high electrical potential. That's when it accelerates. So here we have an increase in electrical potential of 115 volts. Remember, the opposite is true for positive charges. Now, so what does this mean? So this charge is going to undergo an increase in electrical potential energy. And the corresponding increase in electrical potential energy is going to result in a decrease in electrical potential energy. That decrease in electrical potential energy is just the charge times the change in voltage. And in this case, the change in voltage is given 115 volts, and the charge is the charge of an electron is minus 1.6 10 to the minus 19 coulombs times 115 volts. Now, conservation of energy. What does conservation of energy say? Change in kinetic energy plus change in potential energy is equal to 0. Now, change in kinetic energy is going to be 1/2 of mv squared minus 0. V is the final speed. The change in electrical potential energy is what we just discussed here. It's going to be minus or plus minus 1.6 10 to the minus 19 coulombs times 115 volts is equal to 0. The mass of an electron is 9.1 10 to the minus 31 kilograms, so we end up with 1/2 times 9.1 10 to the minus 31 kilograms times v squared is equal to 1.6 10 to the minus 19 coulombs times 115 volts. So I can solve for v squared there. I'm going to use the calculator on the side. So 1.6 10 to the 19 minus 19 times 115 multiplied by 2, that's half to the other side, divided by 9.1 10 to the minus 31 kilograms. That's my v squared. That gives me a large number, and I take the square root of that. Okay, and I end up with, I am having to read how many digits do we have? 1, 2, 3, 4, 5, 6. So V is 6.36 10 to the 6 meters per second. It's quite a high speed, if you notice. It's a lot less than the speed of light, that's 3 × 10⁸ meters per second, but it's not tiny by itself. I'm checking here my 1, 2, 3, 4, 5, 6. That's correct, I think. Okay. So that's this first example. Let's look at the second example here. The difference in potential between the accelerating plates of a TV set is about 26.5 volts. So delta V is 26.5 kilovolts, 1000 volts. And they tell us that the distance between the plates is 1.70 centimeters. And they are asking us to find the magnitude of the electrical field in this region. Okay, now the question here is what we discussed earlier in another recording. When I have an electrical potential here, V1 and V2, we said the electrical field is going to be pointing towards the lower electrical potential. Now, if V2 is higher than V1, it's going to point that way. Now, if I'm going to take a charge and move it from V1 to V2, okay, assume that we are taking a positive charge or a charge Q. Now, if it is a positive charge, the electrical force is going to be in the same direction as E, and I'm going to move it from V1 to V2. So the work done by me is going to be QE times D. The change in electrical potential energy of the charge is going to be QE times D. And the voltage, the change in voltage is going to be, the change in voltage is going to be the change in electrical potential energy over Q. So it's going to be E times D. So in this case, what we are saying is our change in voltage is just equal to the electrical field times D. So in this case, to find E is just delta V over D. Okay, let me try to erase this to have space. And that's going to be 26.5 10 to the 3 volts over 1.7 10 to the minus 2 meters. Okay, so here 26.5 divided by 1.5 it's 17.7 10 to the 5 volts per meter. That's my electrical field. Okay. In this example here, it is asking us to calculate the electrical potential at point A due to charges, the 7 microcoulomb charge, then due to the minus 3 microcoulomb charge. Okay, here it is guiding us through the process. Okay, so I calculate the electrical potential due to the 7 microcoulomb charge. What is it going to be? It's going to be the expression for electrical potential is K Q over R. My R is going to be this distance. Now here this is 3 meters, that's 4 meters. So we're using the Pythagorean theorem. 3 squared plus 4 squared is 25. Square root of that is 5 meters. So my R is 5 meters. So that means my V7 due to the 7 microcoulomb is going to be 9 10 to the 9 newtons meter squared per coulomb squared times 7 microcoulombs, so that's 7 10 to the minus 6 coulombs over 5 meters. Okay, so we can probably calculate this without using our calculators. 7 times 9, 63. 63 divided by 5. I'm using a calculator here. 12.6. 12.6, and we have 10 to the 3. So it's 12.6 10 to the 3 volts. Now, due to the 3.5 microcoulomb charge, we still have the same distance, 5 meters. We are using the same expression, so it's going to be 9 10 to the 9 Newton meter squared per coulomb squared times 3.5 10 to the minus 6 coulomb, but it's a minus charge now, so I have to include the negative sign, over 5 meters. And that's going to be equal minus 6.3 10 to the 3 volts. The overall voltage is the sum of both V7 plus V3.5, which is going to be 12.6 minus 6.3 times 10 to the 3 volts, which comes out to be 6.3 10 to the 3 volts. Okay. In this question here, they are asking us how much work do we have to do to bring a 2 microcoulomb charge from far away to point A. We just calculated from the previous screen that the electrical potential at point A is 6.3 10 to the 3 volts. Okay, since we know that now, so we know that the electrical potential here is 6.3 10 to the 3 volts. Okay. Now, we could have calculated this by calculating the work done to bring the charge, calculating the work due to the plus 7 microcoulomb charge and plus the work due to the minus 3.5 microcoulomb charge. But it is just easier to remember that the work is going to be just the change in electrical potential energy. When our charge is far away, its electrical potential energy is 0, its voltage is 0. It's going to move to a position where it's going to where the voltage is going to be 6.3 10 to the 3 volts. So the work done is going to be just Q times the change in voltage, which is going to be 2 10 to the minus 6 coulombs times the change in voltage, which is 6.3, 10 to the 3 volts, which is just 12.6, 10.6, 10 to the minus 3 joules.